So when it comes to IoT data, not only is it important to have the data, but it's important to be able to trust the data. Is the data valid? Can I trust it? Today on the IoT Show, I have Akshay from Microsoft Research and Ryan from the Azure IoT Developers and Devices team. We're here to tell us everything about Verified Telemetry. That's today on the IoT Show. Hi, everyone. This is the IoT Show. Thanks for joining. I'm Olivier, your host. And today you're here to hear about the IoT sensors data quality and some of the problems around this thing. And for that, I have Akshay and Ryan. Akshay is from Microsoft Research, Ryan from the Azure IoT engineering team. I will start with you, Akshay. How are you?
Hey, Olivier. I'm doing good. It's super exciting to be on the show. Thanks for inviting me.
Always love it when we have collaborations between engineering teams and Microsoft Research. But before we jump into the topic and well, first Ryan's introductions, but the topic then, actually tell me more about your role. What are you doing at Microsoft Research? What kind of projects are you covering these days?
Yeah. So I'm a senior researcher at Microsoft Research. My research interest lies in the intersection of systems and technology for emerging markets, broadly in the areas of AI, IoT, and edge computing. I'm particularly interested in building affordable, reliable, and scalable IoT devices to address various societal challenges. And one of my recent projects is focused on improving data quality in low-cost IoT sensors.
Brilliant and spot on, actually. Well, and we'll see that during the show today. Ryan, you already been on the show previously, but for those who missed that episode, so shame on them first. Now they will have to go and watch it. But can you give us a short introduction of yourself?
Yeah, sure. Thanks, Olivia. Hi, I'm Ryan Winter. I'm a PM in the Azure IoT team. Specifically, I focus on device and developer experience. So this is about helping developers connect devices to Azure IoT. Today, there are a lot of issues with that. It's typically a really hard problem. You have to choose devices, you have to choose RTOSes, use SDKs, and pulling that all together is a hard thing to do. So my ultimate aim is to just make that easier for everyone.
Love it. I'm sure everyone appreciates that as well. So getting devices connected, like you, Ryan, trying to make it easier, and you actually were just starting to describe, some of the things that you're doing, trying to make the data coming from these sensors making sense, or at least to be reliable. So tell me more about, this problem of data quality in the IoT space that we're trying to solve here.
Sure. So the proliferation of IoT sensors and the reliance on telemetry, right, has never been greater and continues to show propensity for exponential growth. We all know that data is the new oil, and customers are increasingly using sensor data to make critical business decisions, right? If you think about it, sensors are the closest source of ground truth, and the data they transmit plays a pivotal role in making these decisions. These sensors are typically deployed in remote locations and in harsh conditions, making it challenging to know if the data received is from a working sensor or a faulty sensor, right? Customers today use expensive and unreliable techniques such as physical site visits, deployment of redundant sensors, or even use of additional contextual information to determine the quality of data, right? The challenge with quality of data, or the lack of understanding of quality of data being collected, is currently being underestimated and leaves our customers driving blindfolded.
Yeah, you don't want that, especially in the IoT space. Things can go wrong really fast. So what is it, Ryan, that you guys have been working on together based on that research work that Akshay's team has been doing? What's happening on the Azure IoT, both SDK side of thing and I guess service side of thing?
Yeah, definitely. So the plan that we're working on right now is to combine the research that Akshay and his team have done and produce this as a service and an SDK that's available and integrated with Azure IoT. So today we're building the Verified Telemetry SDK directly on top of Azure RTOS and the Azure RTOS middleware. So this is something that's going to be deeply integrated with Azure itself. From the device side, people can pick up this SDK, they can build it directly into their device alongside the existing Azure IoT SDKs. They can define a plug and play model. We have direct support for plug and play. And then on the solution side, you can then consume this plug and play model just like you would any other device.
Interesting. Interesting. So before we jump into demos with Ryan, I want to come back to Akshay and try and understand a bit better. So actually, you mentioned that data might come, and you might not really know if it's from a faulty sensor, if it's actual data you can trust, right? So tell me more about that. How did you come up with the logics, the models to determine that a sensor is faulty, that data is not to be relied on, or the contrary, actually?
Right. So before we jump into that, right, let me give you a few customer scenarios, right, what we have been hearing from various customers. One example, right, is on air pollution monitoring. And as we all know, air pollution is a major concern worldwide. To address this, several companies across the globe are deploying hundreds of low-cost sensors to monitor pollution levels, right? And we are closely working with several air pollution companies. And the challenge here, right, is it is non-trivial to detect whether a sensor data is faulty or not, right? First, the bigger problem is faulty sensor readings can mimic a non-faulty sensor data, right? Thus making it very hard to detect failures. And as I said, sensor redundancy can be very expensive, especially when you look at large-scale deployments. And the cost and the logistics involved in sending a technician to remote locations to replace or rectify is very high and also cumbersome, right? And finally, anomaly detectors, right, are not unreliable, as an anomaly need not necessarily imply faulty data unless there is some evidence of sensor failure, right? Due to these reliability issues, the validity and the viability of low-cost solutions, right, have been questioned by various governments across the globe, right? Similarly, imagine a faulty temperature sensor in a data center setup, right, which is used to control air conditioning unit, and relying upon this, right, may lead to taking wrong decisions and can also result in catastrophic event. Right now, more than ever, with organizations focusing on digital transformation, this challenge presents a unique opportunity for us to expand our portfolio to support data reliability as an offering, which we call as verified telemetry.
I like that. And actually, a couple of things you mentioned, low cost. I love that because it's low cost, but it's also what we could call the brownfield scenarios, right? It's things where you already have existing sensors, you already have equipment there, and you don't want to replace that because there's been an investment there. So it's not about like putting some high-end, super, smart sensors that have, as we were saying, anomaly detection embedded in there, whatnot. It's actually about keeping the cost down, but adding the intelligence on top or detecting something is going wrong. But back to that original question, I think the context, you just said is perfect. But like from the pure, electrical perspective, how do you detect a sensor is faulty just by looking at the data?
Right. So our key value proposition, right, is building a very simple and easy way of detecting sensor faults, right? And let's start with, I'm just going to share my slide deck here, right? So the core innovation, what we have developed, right, is basically sensor fingerprinting, where we try to monitor the electrical characteristics of a sensor, right? Let's start with the analog sensor, which basically produces continuous data, right? When the sensor is turned on, as shown here, the key insight, what we have found out is that when you turn off the sensor's response after powering off, right, should follow a characteristic curve when it goes down to zero, right? And this characteristic curve is what we call as fault curve, right? Imagine this fault curve is basically because of the parasitic components and the capacitance present in the sensor, which turns out to be unique for each sensor type, right? Mm-hmm. Now, the key insight what we have, right, is fault curves can be used to distinguish a faulty sensor compared to a working sensor. As shown here, the fault curve has a very distinct pattern for a working sensor as compared to a faulty sensor, right? And similarly, for a digital sensor, our key insight here is to monitor the current drawn finder sensor to determine a working profile of a working sensor. Here is a current profile of a working sensor, and our key hypothesis, right, is that when a sensor goes bad, its physical properties also change, and those are reflected in the current consumption of the sensor. Typically, when a sensor goes bad, its current consumption is completely distinct compared to that of a working sensor.
Okay, so I understand that now that we have these fingerprints for what a good sensor should look like, now we're more able to detect what a faulty one looks like. I would like to turn back to Ryan and understand, how that looks like from the SDK's perspective. What should our Azure RTOS and Azure IT developers expect to be doing to benefit from verified telemetry features like that?
Yeah, thanks, Olivia. So I'm going to do a demo now to show sort of the different SDKs, and I can show sort of how this integrates with our solution. So here is we have 3 repositories right now. We have the Verified Telemetry SDK itself. We have a device sample repository, and we have a solution sample repository. So I've already checked out these repositories in advance to save a bit of time. So what I'm going to do first is I'm going to configure, and I've already deployed a hub. We have an IoT hub, and I've created a device. So I'm going to configure the device and do a build and flash the device. I can do this just within VS Code.
Nice. Well, it's doing that. So you're actually compiling an Azure RTOS, firmware for a specific hardware right now.
That's right. So yeah, this is an Azure RTOS application that uses the Azure RTOS middleware to connect to IoT, and it also is using the Verified Telemetry SDK.
Okay.
So this is going to flash to the device. And this will take a minute. And then I have a second VS Code here, which is the solution sample. So the solution sample is a series of Docker containers. So it's super easy to deploy. So as you just need to install Docker on your desktop, and you just need to configure this device, this file to connect to your IoT hub. And then I can just simply, I can just bring this up. So this is actually just going to build the Docker containers and deploy them on my machine.
Got it. And so I don't know if you mentioned that, but all of what you're showing right now is available on GitHub repos that people can go and check it out to learn how Verified Telemetry is implemented on actual device with an actual solution in the backend. That's
right. Yeah. So back here, I've checked out the device sample, which is this repository, and then the solution sample.
Sounds good.
So the solution sample is up and running. So I can come back to my browser, and hopefully I can load Refiner up.
There you go.
So I'm just going to log in. And so this is our dashboard.
Okay.
Right, and we can see that the device is streaming data, where I have 2 moisture sensors attached to my device, and they're just streaming data, and I can see that if I put my hand over the devices, I can see these devices are responding. The orange dots just means that the data as of now is unverified, so there's no fingerprint collection. So the first thing I would do would be to this is a brand new device, so I want to collect the reference fingerprint. So this is the fingerprint that we deem as the fingerprint that is correct. So I know my device is correct. I know my sensors are working. So I'm going to collect a fingerprint in this good state. So I'll collect the fingerprint for the first moisture sensor.
And interestingly, so you're doing that on both because every single sensor, and actually I think you mentioned that every single sensor is very specific, right? It has its own characteristics that requires you capturing a fingerprint every single time you have a new sensor out, right?
Yeah, that's right. I mean, I happen to have 2 of the same sensors, so this is less important. But typically you would have different types of sensors. And you're right. Each sensor will have different characteristics. So each has its own fingerprint to identify itself. So I can now see in sensor 1 that the data is green, which means that I've collected the fingerprint, the reference fingerprint. And every time I collect a new telemetry point, I'm collecting a new fingerprint and comparing it to that reference fingerprint. And everything is working well.
So it's continuous learning, right? Basically.
Well, so it's continuously evaluating the sensor. So it's continuously looking at the new fingerprints it's collecting and comparing them to the reference fingerprint, which we know is a good fingerprint. So if any time the fingerprint that it's collecting differs from the reference, we know things are wrong.
Got it.
So we can now see that both the sensors are working and collecting green. So the first thing I wanted to do next was to demonstrate a fault. So the first thing I'm going to do is just disconnect the sensor completely, so we can see that. So I'm going to disconnect, I think it's sensor 1. So this sensor is no longer connected. So if we wait for a few seconds, we'll start to see faulty data come in. And this is going to demonstrate a fault that Verified Telemetry detects, but it's also a visual fault. Like you can tell, so I can see on soil moisture 2, we can tell that this sensor is now not working. It's giving like values that are much different from an expecting sensor. So this is a scenario where Verified Telemetry picks up the fault, but this is also something you could pick up by yourself, like if you were visually looking at the data. So this is something that normally today people would look at this data and be like, oh, that sensor's faulty, I need to do something about it. So this is not a particularly interesting scenario. So I'm going to reconnect the sensor. The next thing I'm going to do is I'm going to trigger a fault on the sensor, which is maybe not so easy to tell visually, but verified telemetry should still pick up the problem. So I can see that the data is, wait for this plot to update. The data is now green again, and everything is working along. Yep. So I'm just going to disconnect the ground pin, and let's see what happens to the sensor.
What happens for those who are not familiar with that? If you disconnect the ground, so you still have data flowing, but the data is no longer reliable, right?
Yeah, the data is referenced to ground. So if your ground is floating, your data is just, it has no way to correctly reference itself. So the ground is floating, so it's just going to start producing data that looks the same.
Mm-hmm.
But you can see verified telemetry has said, well, this data is bad, even though really you can't tell. Like if I was looking at this time series, I wouldn't be able to tell that this data is bad. Like obviously over time it'll trend up to some terrible value. So now if I trigger the sensors, I'm going to put my hand back over them again, just to show that. So you can see sensor moisture 1 is responding and it's dropped down to a lower value, but sensor 2 is obviously broken. It's not responding to my my hand's moisture. So this is really demonstrating the value of verified telemetry. We're picking up faults that just wouldn't be, you wouldn't visually be able to tell by looking at the data, and you would have to post-process this and look for a long time and hope that this eventually trends to some value that is unrealistic. Yep. So if I plug this back in again, we'll show that we'll show that the data becomes good. And this is a relatively simplistic fault. I mean, this fault could happen. Your sensor might have a faulty wire and maybe things aren't connected quite well enough. But there are many things that can go wrong with these sensors, and some of them are visually easy to tell, but a lot of them aren't. And with verified telemetry, we're really hoping to capture all the faults that can be detected on a sensor.
I love it. So before I jump into a couple of more general questions, I have a couple here in terms of really understanding how things are working under the hood here. So the SDK part is running on the device. What's its responsibility? Is it collecting more information and then sharing it with the cloud where analytics happen on that fingerprint? Or where are things happening actually right now?
Yeah, so as of today, everything is occurring on the device. So the device is toggling the sensor on and off. It's sampling the data coming from the sensor to generate the fault curve, which Akshay presented earlier. And then it's collecting the operational fingerprints, and on the device itself, it's doing the comparison of the fingerprints.
Okay.
So, and this is something that there's been a lot of effort that Akshay and his team have put together to make this algorithm, this fingerprint comparison, something that can occur on a low-power chip. And that's what happens today.
And that's, I was about to ask, like, it's not about like storing much data directly on the device or actually adding machine learning algorithms directly on that little microcontroller. Is really about being smart about analyzing that full curve that actually described.
That's right. Yeah, running a machine ML model on the device is probably not realistic in many situations. So this is using more of a statistical comparison. But it's interesting you bring up a machine learning comparison, because in the future we do plan to provide the ability for the fingerprint to be shared into the cloud, and then potentially have a model there that can do a more in-depth comparison and prediction of the device's sensor's health. This is something that we're looking at in the future.
I like that. So basically in the process, when you clicked, capture fingerprint, that sent a command out to the device SDK reacts and say, okay, now I need to capture something that's my reference, and on. And after that was actually comparing, data coming in. And so when it sends telemetry, does it send it with a property, with a specific tag that indicates, say this, I'm not sure about this is faulty data?
Yeah. So that's right. So the telemetry is coming in from the device, and what we're doing today is we're attaching some properties to that telemetry stream, which is telling us what the status of the telemetry, the sensor data in that telemetry stream is. So we're using that method. So every data point in this time series has an associated property which tells me the status of that data point. And this data eventually goes through Hub and gets stored in the Event Hub, and you can process this afterwards, and all that data is still valid. The second thing we do use a device property which broadcasts the status of the sensor at a single point in time. So at any point in time, I can look at the device twin and I can see that soil moisture 1 is working, soil moisture 2 is working, and I can see the overall device status. So we have those kind of two methods today. Okay.
And so I had a couple other questions, like they were triggered actually by the conversation right now about cold pass versus hot pass. My understanding then is that this notion of faulty data comes along with the data, so you can actually store for later analytics, but you can also benefit, and you're showing that in Grafana right now. You can benefit from real time, notification that this data is faulty because it comes along with the telemetry, right?
Yeah, that's right. We wanted to make sure we enable both paths. So, the storing the status with the telemetry is obviously, useful for processing this data after the fact. Like you might want to pull in a weeks of data, but you then might want to eliminate all data points that the sensor is deeming as bad. But we definitely want to be able to enable the hot path, and you can monitor the status of the device in real time by looking at either telemetry stream or looking at the device properties, which broadcasts the status of the device.
Love it. We're showing here a demo using Grafana because it's super practical for showing real time, changes and so on. What about integration into other products like IoT Central for verified telemetry?
Yeah, definitely. These are conversations we're having today. The Grafana solution is using our Node.js SDK, the Azure IoT Node.js SDK, which is the same SDK that Central uses. So when we start to look at Central, we want to do integration points like integrate with their time series. We want to be able to make sure that you can trigger rules of the status of the devices themselves. And these conversations we're having today with Central and TSI and other cloud components of Azure IoT.
Okay, last question for you, Ryan, again. So we are seeing the SDK deployed on an Azure RTOS device. Not everyone is using Azure RTOS. Is the SDK available and can be used on other types of devices that are running something different?
Yeah, so as of today, the SDK is split into two parts. We have the core component, which is doing sort of all the heavy lifting in terms of fingerprint collection and comparison and storage. And then we have a middleware layer, which is available for Azure RTOS. In the future, we plan to extend this to include a free RTOS specific port for the SDK, but also we want to make sure we can support people that don't want to use an RTOS. So we want to simplify the core component so that people can easily integrate that into their bare metal samples.
I love it. Okay, guys, it was a very insightful presentation of verified telemetry, how it can be used. Actually, it was super interesting to actually learn how easy, at the end of the day, it is to detect the sensor is faulty, right? Not that hard.
Yes, and it has been a brilliant collaboration, right? To take that simple research idea into converting into an SDK, right, which can scale and can be deployed by numerous customers. And it's pretty exciting moment to see this technology reach customers through verified telemetry as an offering from Azure IoT.
Yeah, and I would expect more to come from your collaboration, right, or like from MSR and Azure IoT product team, because focusing on providing solution that simplifies IoT developers and manufacturers' life, and the other hand, keeping their cost low by implementing solutions that solve real problems, but keep the BOM of their devices down to what they have today. That's pretty good. So if you want to learn more about verified telemetry and check out the GitHub repo that Ryan just showed here, you can go to the aka.ms/IoT show/verified telemetry link that we're gonna pop up right now. And then, well, don't forget to subscribe for the IoT show, and don't forget to come back and see more of these. Actually, Ryan, thanks a lot for joining today. Hope to see you soon. Bye.
Thank you.
Thanks for having me on the show.